approach to approach to calculations for astronomical problems utilizes CPU. Sometimes astronomers are using parallelization and use multiple nodes, but at the end, the bottom line is that it still uses CPU. And for example, if you look carefully to the rebound package, which some of you might know, rebound is a Python package with number of integrators available, and it's really easy and straightforward to use it if you need to calculate the orbits of celestial bodies. And it's well known, and it's very stable and it's very good, but it also utilizes CPU. And when a person asked the creator of this package, the creator of Rebound, whether they plan to support GPU, the answer, you can actually see it on your screen. The answer was that there is no plan to support GPU or other types of optimizations because, quoting, there are only few special cases. I would like to challenge this statement, and I would like to state that there are much more where you can utilize GPU and other types of optimization and significantly improve, significantly boost your calculations, even if you use just one computer, one laptop, or one server. So the overall goal is to show that the transition from traditional approach, from CPU-based approach to GPU-based approach, or anything similar, is really straightforward. It does not require any significant development, or of course, it might require some significant development if you use some tools that do not allow to switch smoothly. But if you use Python or if you use C++, there are many straightforward approaches how you can start using GPU instead of CPU and boost productivity. So I would like to mention two tools. I'm using primarily Python as a primary language because it allows me to develop and run experiments faster. Faster not in terms of time, but in terms of, not in terms of computational time, but in terms of time I'm spending to develop a new piece of code. So hence I'd like to mention two tools. The first one is PyTorch, and the second one is TensorFlow. I'm pretty sure that many of you have already heard about these tools. However, what is really important for this talk is that both tools support very simple transition, very straightforward transition from CPU to other types of devices. And I would like just to show you an example of how one can start utilizing these things for astronomical problems. So here is an example of how one can enable acceleration just with one line of the code. It is below in the bottom of the screen. In this particular case, actually, I use two different stuff in terms of machine learning. Traditionally, in astronomy, we are using a classical machine learning with supervised and unsupervised learning, which is based mostly on some statistics. Last years, a lot of studies introduced also the usage of deep learning networks, which is also amazing stuff and interesting. But if we review the market of machine learning applications for, let's say, last couple of years, we could find that another type of machine learning applications was growing very rapidly, especially this year. I'm talking about large language model. Of course, it's not obvious of how one can use large language model in astronomy because, I mean, it's clear when you perform some studies in social sciences like sociology or linguistic or psychology, because they are dealing with texts, and therefore large language models could be natively used for such type of research. However, when we are talking astronomy, the question is whether we can use it, whether we can utilize. And here is a very simple example of how one can use large language models, more particularly ChatGPT, to significantly simplify the workflow. I didn't want actually, for this example, I wanted to develop a very simple agnostic application that just integrates an orbit of a celestial body within the solar system by using very simple implicit Runge-Kutta method of fourth order. It was just a test task, but I didn't want to write any piece of code. I wanted ChatGPT to write the code on my behalf with all the optimizations I've talking about, with optimizations to GPU device. And that's actually what you see on my screen. So I was just able to specify the task I want to accomplish. I added some requirements like usage of GPU, and that's it. I got the piece of code, which I adjusted a little bit, but the bottom line is that I was able to improve my performance as a developer for this particular task by using large language model. So I think as a conclusion here, when we are talking about machine learning approach in astronomy, there are some implicit stuff like using of LLM that could simplify many of the workflows we are using on daily basis. And just adding this one string where we map the whole application to GPU device significantly boosts the performance. And let me just show you a few calculations. I just want to mention here that it's not like a very accurate experiment. I've run it on one laptop, on my laptop, and on one GPU unit. So therefore, if let's say it would be a scientific paper, I would have to make more accurate experiment. So therefore, these numbers might vary a little bit. But even if we just check these numbers, like here, for example, the first line is about Runge-Kutta method of fourth order that integrates just one object. I didn't use the calculation, the estimation of one object, because when you need to start a program and when you need to perform some basic stuff before you start actual calculations, it takes some time. And this piece of the software is rarely optimized for GPU because it's just reading some inputs, reading some data, downloading some data, like in this particular case. So it's not clear when you get some numbers for just one object. So it's better always to test on multiple objects. And here's an example below the second string with 100 of objects. And as you see, a simple adding just one string, which maps the application to the GPU device, improves the speed in something like 22 times. There is also one more column here, which is called MPS. And it is very useful for those people who are using MacBooks or Apple devices, because they have different architecture. You cannot use GPU on Apple devices. However, if you just use it like I use it for my experiments, when I don't need a lot of calculations, when I just run a few of them, I can still speed up the execution time. And here, I mean, if I just use rebound, like I regularly do for some of the calculations, it will be from 3 up to 5 times slower, rather than I'm using MPS device. That's, again, just one string that you can add to your program, which significantly boosts the performance. While it is not very important for large computations, you can run multiple computations on multiple devices, but when you test something, you still spend some time. And if let's say you have to wait a few minutes before you get the result and could verify them and then run another experiment to test the software you have created, etc., etc. If you spend less time even on this testing and debugging stuff, you still get better productivity. That's the point. So with PyTorch and TensorFlow, you can run not only on GPU, but also on MPS, Apple Silicon chip devices. And if you use them for your own purposes, you can boost your development significantly. I have also tested the same approach, not only on integrating the orbits, but also on some other tasks, which are pretty common when you perform some experiments with small bodies in solar system. I'm talking about filtering time series and smoothing time series whenever you need them. As you can see from the rows numbers 3 and 4, even for this particular task, when you do not interact with tensors, still there is a significant performance boost in something like from 2 up to 10 times. And it also works. That's the point. So another story might be related to the fact that through the last couple of years, this large language model approach was growing rapidly, which implies that now we have a lot of online services that allow you to rent a GPU unit for very short amount of time. It's a usual problem if you need to perform some calculations, but you do not have a GPU device. It might be challenging to find a good GPU device. You either have to make an agreement with some cluster or whatever. So it might be challenging, even if you, especially for the case, if you just want to run one experiment and check whether there are some interesting results. These days, taking into account that GPU are utilized by many other organizations, you can use different services like Runpod, Hugging Face, Vast, or even Google Colab to rent a GPU unit for a couple of hours, which will cost a few dollars. But in the meantime, in terms of performance, that's a really significant boost. So, for example, when I was running an experiment that aimed to calculate some statistics for the asteroids in the main belt, I had to wait a couple of weeks if I wanted, when I used CPU, because there are a lot of asteroids in the main belt, more than 500,000. And if you integrate the orbit of each of these asteroids, it takes a couple of minutes at minima, and multiplying these numbers, that's really huge. However, I was able to run the same experiment on GPU units, and it took less than a day. So that's significant performance boost, and it's pretty affordable in terms of pricing because you don't need to rent this device for a long time. So overall, I just wanted to share the idea that nowadays, when we are running any numerical calculations on for astronomical problems, it might be a good idea to start thinking about utilizing GPU units instead of CPU, because you can run faster your experiments, you can debug your code faster, you can get results faster, which means that you improve your overall productivity. And as I shown previously, if you use pretty standard Python tools like PyTorch or TensorFlow, it's really easy to start doing that. So I think that's the main point of this talk. Thank you.
Thank you for the presentation. You speak about the transition between CPU and GPU. I would like to ask about the kind of the type of calculation can be passed by GPU, and about the accuracy, the precision, according to or comparing with the CPU based calculation.
Yeah, in terms of the transition, it's pretty native for astronomical problems because if you want to utilize GPU, and if let's say you are using PyTorch, you will deal with tensors. And as you might realize, tensors in astronomy are pretty common. Actually, you can rewrite the equation of motion in tensor form very easily, and you can actually use that. So if you want to, let's say, transform your piece of code which integrates, which is an integrator like, I don't know, Burlish or Everhard, you need just to replace vectors with tensors, and that's it. You don't need to change anything else. In terms of accuracy, it has the same accuracy as if you were using regular Python, because what PyTorch does, it just make another abstraction layer on dealing with tensors. And it uses the same functions as the native Python is using. It means that the accuracy is not affected by this transition. You just replace vectors with tensors, with PyTorch tensors, and that's it. And all the equations.
Any question more? Thank Evgeny again. Thank you, Eugene. We have another remote